The year is 1938, and the world is on the brink of a second Great War. But what is the state of the world of physics? Oppenheimer is currently at Berkeley, having recently been promoted to a full professorship. Einstein is at Princeton after narrowly escaping the chaos of Nazi Germany. Niels Bohr, the creator of the orbital atomic model and founding father of quantum mechanics, is struggling to keep his institute in Denmark running amidst the retreat of Jewish scientists. The cocky young Richard Feynman is also at Princeton, but as a graduate student working towards his PhD. And the so-called Pope of Physics, Enrico Fermi, has just utilized a very unique means of escaping from fascist Italy. After traveling to Stockholm to accept the Nobel Prize, he and his family secretly continued to New York City, never to return home. Adding fuel to the tumultuous international fire, two German scientists, Hahn and Strassmann, have just successfully split the uranium atom nearly in half by bombarding it with neutrons. Unlike the natural radioactive decay that happens randomly within the uranium atom, this catastrophic phenomena produces two vastly different elements from the original uranium, and produces a massive amount of excess energy. This process is what we now know as nuclear fission. So what does this mean for science, and what does it mean for the world? Well, from a scientific standpoint, this was the first evidence that nuclear fission could be induced manually by utilizing natural radiation. In other words, some heavy isotopes, such as uranium, have too many neutrons in their atoms. Imagine that the strong nuclear force, which holds the protons and neutrons together, is like a belt, and that it only goes up to a certain size. These heavy nuclei are called unstable because they have the potential to burst the belt at any minute. Unstable nuclei will randomly undergo decay, meaning they pop and fire off other particles, such as neutrons, and some energy. Neutrons are special because they have no electric charge. This means they can fly around inside a chunk of material without getting deflected by the charge of other atoms. Thus, after being fired off from an unstable atom, they can hit other atoms and pop their belts. The discovery of fission means that this random decay can be harnessed as another tool for scientists and engineers, one that has the special ability of neutrons to pierce to the very heart of the atom. What does this mean for the world? Well, the fact that nuclear fission produces a large amount of energy compared to the energy that was put in to cause it means that it has a net positive energy. As you may have realized, net positive energy means that it can serve as a fuel source, hence the viability of nuclear energy as a way to power our homes and cities. If you can keep these reactions going and produce energy at a macro scale, you can get out more energy than you put in. However, the idea that it can create enough energy to power a city if used in a controlled way also implies another more sinister possibility. If used in an uncontrolled manner, the potential for destruction could be unlimited. That which can be used to power a city can also be used to destroy it in the blink of an eye. With that being said, as scientists began to realize the different possibilities presented by the discovery of fission, they also noticed that both ideas require something that hadn't yet been performed: a self-sustained nuclear chain reaction. Imagine you have cups scattered out on a table as though you are playing Pong. In your hand, you have one ping pong ball. Your goal is to bounce the ball on the table and make it land in one of the cups. By landing the ball in the cup, you get 1 point. Intuition tells us if you bounce the ball as hard as you can, then it's just going to fly off the table and will have basically no chance of landing in a cup. However, if you carefully bounce the ball with just the right amount of force, you can have a pretty good chance at landing in one of the cups, especially if they are arranged close together. Another twist on the game: if you manage to make the ball land in one of the cups, you suddenly get 2 balls back. Now you get to throw both of those into the cup, and if you make those, you will get 2 more balls back for each one that you make. As you may have already realized, this game will quickly get out of hand. If you have your throwing technique locked in and the cups stay tightly packed, you should continue making your throws and getting more balls back until you have more ping pong balls than you can handle. And as you continually throw more and more balls each round, your score will skyrocket. This game can serve as an oversimplified analogy for how a self-sustained nuclear chain reaction can occur. The ping pong balls represent neutrons. These neutrons are randomly produced by the radioactive decay of uranium. However, when the uranium decays, it sends these neutrons flying off in an indiscriminate direction with too much speed. This is what happens when you bounce the ball off the table as hard as you can. During his work in Rome, Fermi discovered that, in order to slow the neutrons down, you need something called a moderator. By passing the neutrons through a moderator, you can slow them down to a manageable rate, which corresponds to you bouncing the ball carefully and aiming towards the cups. The cups in this analogy represent other uranium atoms. If you can manage to sink one of the balls in a cup, that means that the neutron managed to hit one of the atoms. This causes the production of two more balls, aka neutrons, and also gives you a point. The point that you get represents a gain of energy. So to summarize, just like in the game of Pong, in order to make a neutron capture on another atom, you have to slow the neutron down with a moderator, pack in the atoms or cups tightly enough so that you won't miss, and aim carefully. If you make the neutron in the atom, then you get two more neutrons to play with, and a point's worth of energy. So, if you keep scoring, you keep playing, and each round produces more and more energy. You have two options when it comes to what to do next. You either just keep playing as long as you possibly can until you get so many ping pong balls that the cups fill up and fall over, and you can't keep track of your score anymore, or you set a healthy limit for yourself, and you play slowly and at a steady rate. The former situation represents a nuclear bomb, while the latter represents a controlled nuclear reactor. As the daring experimentalist, Fermi took on the challenge of creating the first man-made chain reaction. His idea was to use graphite as the neutron moderator and uranium as the fuel. Using his own theoretical calculations, Fermi figured out how he needed to arrange the chunks of uranium and graphite to create the perfect balance between neutron moderation and fission. Additionally, he used control rods made of cadmium, which was capable of effectively absorbing neutrons. These were used to control the power of the reactor. By inserting or retracting the control rods, they could decrease or increase the rate of nuclear fission. Famously, the last failsafe to ensure nothing catastrophic happened was known as the scram line. The scram line consisted of a control rod suspended by a rope above the reactor, which, when the rope was chopped by an axe, would fall into the reactor and completely stop the chain reaction. This prototype nuclear reactor, known as the Chicago Pile 1, was built on a racquetball court under the old football field at the University of Chicago. As expected, due to the experimental prowess of its creator, the pile would work exactly as planned. It sustained a steady nuclear chain reaction and produced about half a watt of power. Thus began the race to create both nuclear energy and nuclear weapons, which never would have been possible without the nuclear chain reaction. I hope you've enjoyed this edition of Seasoned with Science, and I encourage you to leave a comment with what scientific topic you would like to hear about next, or a recipe you would like to see. And, as always, don't forget to season your food with your heart and to season your mind with science.